name is Juliana, and today I'll be presenting my Data 690 capstone project, which is my AI wardrobe stylist. This is a personalized outfit recommendation system that uses multimodal retrieval and LLM reasoning to suggest outfits from my actual closet based on my mood, occasion, and the current weather. So here's the roadmap for today. I'll cover the problem definition, the project scope, why this project matters both personally and technically, the system architecture, some non-obvious design decisions that I want to highlight, and where I am in my implementation and what I've learned so far. So let me start with the problem. Getting dressed sounds trivial, but it's actually what I'm calling a retrieval and composition problem that most people, including myself, solve kind of poorly every day. So every morning you have to mentally inventory your wardrobe, filter for weather, occasion, how you're feeling, and assemble a combination of individual items that work as a coherent outfit, all usually under time pressure. There's actually data to back this up. Research by Fashion United found that Americans leave 82% of their wardrobe items unworn in any given year. And WRAP, which is the Waste and Resources Action Program, found that the average adult actually owns 118 clothing items, and a quarter of those haven't been worn in over a year. So the problem isn't that people don't have clothes, it's just that mentally searching your full wardrobe and composing an outfit from it is demanding enough that most people just default to their same small rotation of familiar outfits while the rest of the wardrobe just sits there. So if you look at the existing solutions in this space, they generally fall into three categories, and none of these fully solve the problem. So the first is generic style advice from fashion websites and magazines, which give you trend-based recommendations and they can't know what you actually own. Then we have personal shopping apps like Stitch Fix, which suggest new purchases rather than helping you use what's already in your closet. And then there's manual wardrobe organization apps like Stylebook that let you catalog your clothes, but there's no intelligent retrieval, no outfit logic, no weather awareness. When I was thought of this project, I did find an existing app called Alta, which was named Time Best Invention of 2025 and has been featured in Vogue, Fortune, and Elle, which lets you photograph your wardrobe, creates a digital closet, and generates outfit recommendations informed by the weather and the occasion. So the existence of this app, I feel, actually validates that the market for this tool is real, and I'm not trying to compete with Alta in any way. This is really just an academic implementation that builds the same kind of system from scratch, so I can understand how it works under the hood. I also just think it's really neat. So before I go any further, I want to cover the scope because when I first thought of this, I had so many ideas. On the left, you can see what is in scope. So that is a single user system for my personal wardrobe, 105 of my clothing items in 5 categories, a natural language, mood, and occasion prompt, real-time weather via OpenMeteo API, per category semantic retrieval, LLM outfit composition with an explanation, all run on Google Colab with free T4 GPU. On the right are the things that I very excitedly came up with but deliberately scoped out. So that includes multi-user support, mobile interface, user feedback, ratings, Google Calendar integration, virtual try-ons, accessory recommendations, and many more. These are all really fun ideas, but none of them are feasible in an 8-week span with no budget. So I decided to scope it down to just the primary mechanics of this project. So this project matters to me on 2 levels. On the personal utility side, those wardrobe utilization statistics are my actual life. I would say I wear about 20% of my closet regularly, and I would just love a system that knows my wardrobe and my context to prevent me having to dump half of my wardrobe on my bed to prepare for an event, and I'd love to use more of my closet. On the technical side, the architecture that this system requires actually mirrors what companies across the industry are building right now and what's in demand over private data. So I'm using RAG, which is Retrieval Augmented Generation, and it's the most in-demand architecture for deploying LLMs in real-world settings. Agentic AI job postings grew 280% year over year, according to a 2026 analysis by Jobs by Culture. And that's what this project develops. Building a pipeline over a private corpus, integrating external APIs, and prompt engineering and compositional reasoning are exactly what those roles require. So here's a user-focused overview of the system architecture. We've got the user doing a one-time upload of all their clothes, and then each time they want to generate an outfit, they input a prompt, and the system fetches whatever weather is in the city they've stored as their primary city, and then the system processes this information and generates a sensible outfit from the user's own wardrobe pictures. Now, what is in that processing step? Here's the full architecture. So the system splits into two different phases, the offline or one time on top, and the online or each request on the bottom. In the offline phase, which runs once per clothing item, we have clothing items, photos that are loaded from Google Drive and pass through two models in sequence. First is WIP2, which is a vision language model from Salesforce, and this generates a plain language description of each item covering the color, fit, fabric, and formality. Then we have Fashion Clip, which generates a 512B vector embedding for each item. Both of these are stored in a ChromaDB vector database in Google Drive. This phase runs once, and the results persist across sessions. I chose Fashion Clip because it was pre-trained on 700,000 fashion product images to give it fashion knowledge off the shelf, which will help shape the quality of the embeddings produced. In the online phase, which runs every time I want an outfit, my natural language prompt and a live weather API call come in as two inputs. So Fashion Clips converts the text prompt into a vector in the same embedding space as the clothing image, which I'll go over in more detail later. And then we execute a cosine similarity search per clothing category and return top 3 candidates per category. Those candidates, along with their descriptions and the weather context, are passed into an LLM, which reasons about color coordination, formality, weather appropriateness to compose the final outfit. Then the output is the actual photos of the selected items alongside a plain language explanation. So my two data sources are my personal wardrobe and the OpenMateo Weather API. My wardrobe is 105 items across 5 categories, which are 48 tops, 19 one-pieces like dresses and jumpsuits, 18 outerwear items, 12 bottoms, and 8 pairs of shoes. I excluded accessories like jewelry and hat to keep the scope manageable. OpenMateo is a completely free open source weather service that aggregates data from over 15 national weather services and requires no API key or account. I will retrieve 4 fields at query time, so that's the temperature, the weather code, the wind speed, and precipitation probability. This data is not stored. It's going to be fetched every time there is a query. One note on weather code, this is just a coding system that can be mapped to a natural language description. So for example, 3 maps to overcast. So we have 3 open source models here doing the work. It's worth talking about each one. WIP2, like I said, is from Salesforce and just runs during the offline phase. It's a vision language model that will take the clothing photo and generate a detailed text description, which will give Llama the information that it needs to reason. Fashion Clip runs in both phases. In the offline phase, it generates image embeddings, and at query time, it generates a text embedding from the prompt. Because it was fine-tuned on fashion data, it understands fashion-specific vocabulary and visual concepts better than other clip models that are out there. That's the theory anyway. Llama 3.8b from Meta is going to run at query time, and this is what's going to make the final call on the outfit. It's going to receive the top candidates per category with their blip descriptions and the weather context into a single prompt and generate a coherent outfit. Llama is just going to decide which clothing items actually work the best together. All of this is going to run on Colab, and there should be no API costs. I want to spend a minute on cosine similarity because it's the math that the retrieval step uses, and it's not something I was familiar with before this project. So every clothing item in my wardrobe is going to get converted into a list of 512 numbers, a vector, that represents its visual and stylistic meaning. I've made a 2D visual here on the slide, but this is actually in 512 dimensional space, which unfortunately cannot be fit onto a slide. But the text prompt is also going to get converted into a vector in the same space. And cosine similarity is measuring the angle between two vectors. A small angle means similar meaning, and a large angle means different meaning. On the right, you can see that my red vector is my prompt, which is relaxed brunch, and the teal vector is a pair of linen trousers. It's actually the photo that was converted into a vector. And we also have another photo converted to a vector of a tuxedo jacket. Because they're embedded into the same vector space, we can do this semantic search. So if the angle is large, they're very semantically different. If the angle is small, they're semantically similar. In this case, linen trousers has a much more similar semantic meaning to relaxed brunch than a tuxedo jacket does. So ChromaDB computes this angle between the prompt vector and every clothing item vector and ranks them, and then returns the closest top 3 per category. One thing to understand is that cosine similarity is not outfit compatibility. So in this case, it's telling me which individual items are matching the vibe of my prompt. It's not telling me whether those items work together as a combination. So that reasoning is going to be delegated to the LLM with the top 3 candidates per category, which are tops, bottoms, outerwear, etc. I wanted to highlight 4 design decisions that weren't obvious and required some additional thinking to arrive at. First is why search per category instead of just across the entire wardrobe. So if you run cosine similarity across your entire wardrobe at once, the top 5 results might all be tops. And because in my case I own 48 tops and only 8 pairs of shoes, that might be likely actually. So running the search separately per category guarantees a balanced candidate pool for the LLM to compose from. Second is, why did I store blip descriptions as plain text instead of as like a structured table with separate fields for color, formality, etc.? The main reason is that we're using an LLM for this reasoning step, so having an actual phrase like oversized black graphic tee made of cotton, it's cropped and casual is more useful for reasoning about pairing than just giving it like color equals black, fit equals oversized as separate structured fields. And it also gives blip the flexibility to describe the item with more language if it's merited. Third is fashion clip versus base clip. I briefly went over this earlier. As I said, fashion clip was fine-tuned on 700K fashion images. A little more context there, is actually trained on fashion catalogs, so it received pictures of clothing with catalog style descriptions, which is what I'm trying to replicate with these blip descriptions. And so I feel that makes it a better candidate than general purpose clip, but that remains to be seen in the actual implementation. And then why split into offline and online phases? The main reason for this is that it just makes more architectural sense. It's better to preserve memory this way, but also I'm using free collab, and we can't be holding these 3 huge models in memory simultaneously. So having an offline phase where we load and unload the models as required, save things to Google Drive, and then only load what we need at query time makes more sense efficiency-wise, and it's also the same architectural split that production RAG systems use. So here's where I stand. The offline database creation phase is mostly complete. All of my wardrobe items have been photographed and organized in Google Drive. Lib2 descriptions have been generated and manually reviewed and corrected for accuracy. And I've set up ChromaDB with all of those descriptions. The next steps are to generate the embeddings with Fashion Clip for all of my clothing items and append them to the existing records. And then I have to build the entire online query pipeline. So that's text embedding at query time, cosine similarity search, and outfit composition. And for that LLM phase, I'm going to have to do iterative prompt engineering across test scenarios, and finally finish out the course with Unit 8 report. 3 lessons learned so far are scope, scope, scope. When I originally thought of this, my brain was like a runaway train. I thought, wow, it would be so cool if this integrated with my calendar, read the event description, location, proactively suggested outfits, or like, what if it proactively identified gaps in my wardrobe? Like, hey, it would be a lot easier to make nice outfits for you if you had more sandals. Or a user feedback mechanism that shapes the way subsequent outfits are generated. But none of that is feasible, like I said, and it's better to build a proof of concept first with the primary mechanics of the system. Second is that formal requirements are a great tool. Writing requirements in the system shall format was new to me, but I've worked at Meta previously, and I had seen software and ML engineers produce product requirement documents as standard practice before any implementation. And so this just made it very clear that it's a useful tool and data scientists need them too. And it just really facilitates helping the right questions, what data needs to exist, in what format, produced by what process, at what stage. And yeah. Third was model selection is about constraints, first and foremost. There are a lot of open source LLM options out there, and it'd be great to just choose the one that scores highest on standard benchmarks, but it's not really going to work with my hardware constraints using free Google servers in their Colab environment. I wanted to include a just for fun bonus lesson. When I was first implementing this, it was actually not very trivial to get Lib2 to generate outfit descriptions. This top, for example, Lib2 just had so much trouble with it for whatever reason, and the screenshot I included here was maybe the third time I had run this image through the model, and the description it generated was, "See more below. Please also describe the problem. You have taken a picture of clothing that is broken, so it is impossible to tell what you're describing." I wish I had taken more screenshots, but depending on the model parameters I chose, I got responses in different languages or responses that are completely unrelated to clothing and for some reason are very aggressive, like, "I'm really tired of this crap." This has definitely been one of the trickiest but funnest parts of the process. So that's my talk, and here are my references. Looking forward to feedback and discussion. Thank you so much.